In this video, we will learn about cycloaddition reactions, which are a subclass of pericyclic reactions. In a cycloaddition reaction, two different pi systems will react together to create a new ring. In the process, you lose two pi bonds and gain two sigma bonds. Cycloadditions and the opposite process, cycloreversions, are given a nomenclature or an identifier, which is going to look like this right here. So it's a bracket and then a number plus a number. These two numbers indicate the number of atoms that are involved in that cycloaddition. So for example here, this is a 4 plus 2 cycloaddition in which it looks like the 4 carbon atoms of this pi bond are joining the ring, and the 2 carbon atoms here are going to be part of the final ring. So you'll notice that it's not the number of electrons or the total number of atoms in a pi system, just the number of atoms that are becoming part of the new ring. This particular example is a Diels-Alder reaction, which we'll go over in much more detail in the next video. Here's another example of this identifier or nomenclature. So here I have an azide, so that's N3, doing a cycloaddition with an alkyne. That's overall getting me a new 5-membered ring, and so here we have a 3 plus 2 cycloaddition. That 3 is coming from the 3 atoms of the azide joining the ring in the product, and the 2 is coming from those 2 carbons in the alkyne. So you should recall from the introduction to pericyclic reactions that our pericyclic reactions follow selection rules. These specifically Woodward-Hoffmann selection rules that tell us whether a given process is going to be forbidden or allowed. Now that seems a little bit esoteric, and this table right here for determining allowed or not is a little bit weird and hard to connect to the reactions. But I think what you want to take away from this is that really there's always two choices. So either we're going to deal with a reaction that has 4n plus 2 total pi electrons involved, in which case you get one set of possibilities, or you're dealing with a cycloaddition with 4n electrons, in which a different set of possibilities is allowed. Of those possibilities, you are either going to have what is called an thermally allowed process or a photochemically allowed process. And this is all very weird, but basically, under thermal conditions, if we have 4n plus 2 electrons, so for example 6 electrons, then our reactions that are going to be thermally allowed are the suprafacial plus suprafacial reaction. And so under photochemical conditions, we would not be able to do our reaction supra plus supra, but rather we would have to do it supra plus anterafacial. And all of that is the opposite for when there's only 4n electrons. So that's, again, maybe not the most obvious in terms of what all of that means. So in general, it's easiest to remember that if we're thinking about the faces of the pi system reacting, it is much easier to do a reaction for a given pi system suprafacial, meaning all on the same side of that pi face. So let me try to show you what this all means in the context of a physical model. So I'm showing you a 4-atom pi system here with 2 pi bonds in it. I don't have enough pieces, so you're only seeing half. So you're not seeing the top half of these p orbitals that make up the pi molecular orbital. Hopefully that's okay. The key thing we want to take away is that we can do our reaction suprafacial, so both my reacting ends of the pi bonds are here, and that's where my reaction would happen. Or we could do this reaction anterafacial, in which case it would be like this, so kind of from opposite ends. And so a reaction should be much easier to do suprafacial to suprafacial like this, right? So you can kind of imagine that this is much easier to get all your phasings aligned and mixing. It's pretty much impossible to do if I'm trying to get one of these to react suprafacially with the other anterafacially. There's just no kind of overlap that we're going to be able to get to make new bonds. So our pattern is that since suprafacial, so let's say suprafacial of this 4-atom piece, and suprafacial to this 2-atom piece, that combination is the easiest one to do, then we'll just use that as our benchmark. So we're always going to look for when that is allowed or not. Right? And so if you take a look at our table here, what you see is that the suprafacial plus suprafacial is going to be thermally allowed when we have 4n plus 2 electrons, and it's going to be photochemically allowed when we have 4n electrons. And so that works out really nicely that our most common types of cycloadditions, which are 2+2 and 4+2, those fall under the photochemical and thermally allowed conditions, respectively. If that wasn't so clear, I just want to do this again in kind of now a drawing form. So here what I'm saying is that I have two reaction components. In an S plus S case, I would be making my bond between those two ends, and you'll notice that on the red pi system, I'm reacting on the same face, so suprafacial. On the blue pi system, again, I'm reacting on the same face, so suprafacial. That's in contrast to this situation where we have S plus A, and our new bond is reacting on, let's say on the red piece, we're going to react on the suprafacial side, but on the blue piece, we react interfacial, which means I have to kind of go like that, which is just physically very difficult. Again, the takeaway from all that is that for 4n plus 2 electron systems, we'll tend to do thermal cycloadditions. For 4n electron systems, we'll do photochemical cycloadditions. Now let's look at some examples of cycloadditions. I'll show you both the conventional suprafacial plus suprafacial type of cycloaddition and also an example of one that does go antirofacial. So the first reaction we'll look at is the thermal 4+2 cycloaddition. This is by far the most common type of cycloaddition that is used by organic chemists. It has its own name. It's a Diels-Alder reaction, and it's common enough that it deserves its own video. So that will be coming up in the future. So here's just an example of such a reaction. In terms of a mechanism, just recall that our pericyclic reactions all go through a concerted step, which means there's only one step. And so our mechanism could look something like this, getting us to our product. And again, remember that these pericyclic reactions, your arrows can go in this direction or they can go the other way around. The reason being that our transition state, which I'm showing you right here, is cyclic, and so we have what looks almost like an aromatic ring in here, right, of all these electrons going around. So I have this example reaction here pulled up, and if I take it and move it around in space a little, what you'll see is that the way that they are interacting with each other during the reaction is not like how we draw it on paper. So they're kind of vertically side by side. The reason for that is that our pi bonds have to be able to overlap. So if I'm doing this plus this, we have to kind of bring our molecules in sideways. It's not like the way we draw it, which is this way. So we're kind of turning our molecules face to face and doing the reaction. So let me play through this reaction here. So if you're watching it, those pi bonds going to come together, and then suddenly you get that momentary transition state where those bonds were not fully formed, and now you have the product. Let me do that again. And I'll move this whole thing around a little so we can take a look at it. So from above now, what we're seeing is the formation of the cyclohexene. And in the way that I drew it, it's this way. And so just to make sure that this does match the expectations of our Woodward-Hoffman rules, I wanted to show you the molecular orbital analysis for this reaction and the next few that we'll look at. The way that we'll do this for cycloadditions is to look at the HOMO of one of the pi systems and the LUMO of the other one. And so this is very analogous to the thinking of nucleophile and electrophile that we had in ionic reactions. And so if I'm looking at my two reactants up here, I would argue that this pi bond has an electron withdrawing group on it, so I'm just going to make this one the one that reacts with its LUMO, and this one has no electron withdrawing groups on it, so I'm going to make it the one that reacts with its HOMO. So kind of like nucleophile electrophile. And so if I go look at my pi molecular orbitals for a 4-atom system like this with 2 pi bonds and a 2-atom system like this, then I can go figure out what my HOMO and LUMO are. I've shown them to you here, so go verify this for yourself. This is the HOMO of butadiene. This is the LUMO of just ethene or ethylene. And so what you see is that what we really care about is the ends of these pi systems. And the ends here are phase matched in a way that allows us to do this suprafacial to suprafacial interaction and thus overall that cycloaddition reaction. The point here is that the 4+2 cycloaddition is thermally allowed because of the way these frontier molecular orbitals have their phases oriented. And so when we're trying to do a cycloaddition, we'll just use heat to run our reactions. Now let's look at a 4+4 cycloaddition, which is going to take place under photochemical conditions if we're doing it suprafacial to suprafacial. Again, it's 4+4 because we have the 4 atoms here and the 4 atoms here. And we know that it's photochemically allowed because if we look at this, there are 1, 2, 3, 4, 5, 6, 7, 8 total pi electrons. 8 electrons falls under the 4n row in that table of selection rules. Often that number will match the 4 plus 4 here, but not always. So just be careful about conflicting the number of atoms with the number of electrons. This is kind of a fun reaction because it actually gets you 2 different products here. So you actually can get either a 2 plus 2 cycloaddition or a 4 plus 4 cycloaddition. I'm going to draw the mechanism here for the 4 plus 4, but you can go in and figure out the one for the 2 plus 2. So here's our 4 plus 4. And you'll notice this is in pretty low yield, but it works. And here's our molecular orbitals. Again, go through and double check this. Since we're under photochemical conditions, one of our pi systems will be in the excited state. So not both of them, just one of them will be in the excited state. And for us in this reaction, both sides are the same. They're both just kind of butadiene-like pi systems, so I'll just use butadiene here. So our HOMO in the excited state is now this pi molecular orbital, which is the pi 3. And the LUMO that I'm going to react with on the other side is going to be also the pi 3, because if it's not in the excited state, then now pi 3 is the LUMO. So on this molecule, I'm going to excite this side. That causes that side to look like so. The other side's not going to be excited. It's going to look like this. And again, what you can see is that now we're nicely meshed up to do suprafacial plus superfacial reaction there. So if you're thinking about reaction conditions here, we just remember that under photochemical conditions, we're adding in all this energy. We're not saying that 100% of our pi systems are going to be in the excited state. Only a fraction of them are going to be, and it's the fraction of them that are in the excited state that are able to do the 4 plus 4 reaction. Here's the promised cycloaddition that has an enterofacial component to it. This is a 14 plus 2 cycloaddition, so there's I guess a lot of atoms here. So looking at this reactant here, we have 2 7-membered rings bridged by an alkene. And we have a nice, very electron withdrawn alkene down here. And if we go through and try to draw the mechanism for this, what we should see is that the bond that's being formed between this carbon and this one here, that's this wedge like so, doesn't allow us to push electrons this way because the pi bond is kind of to the left here. So we have to push our pi bonds this way, and that's why we have to go through all of these pi bonds in order for the cycloaddition to happen. So if you're counting electrons now, we should have 2, 4, 6, 8, 10, 12, 14, 16 electrons here. That's corresponding to a 4n electron system, which means that we would expect that we could do this reaction only under photochemical conditions to achieve the suprafacial plus superfacial reaction. It turns out if you do heat these together, you can get the cycloaddition. And so because that works, that tells us that what's thermally allowed, so under heat conditions, is the suprafacial plus enterofacial reaction. So let's look through the molecular orbital analysis here. And the big thing to realize is that all the 4n systems will have the same phasings at the ends of their molecular orbitals. So the HOMOs and LUMOs will have the same ends, either both phases the same way or phases the opposite way. So I have those here. The 14 pi system essentially looks like this with a bunch more atoms in between. So what that means is that we can take the LUMO of our very electron withdrawn alkene here, and the HOMO, which is going to be the pi 7 of this massive pi system. And that HOMO should have the same phasing of ends as our 2 pi molecular orbitals. So now given the phasings here, you're forced into doing an enterofacial reaction with respect to one of the pi systems. So I'm going to do superfacial on my alkene here and enterofacial on my larger pi system up here. And so what we're imagining is that this large pi system can kind of deflect so that we can squeeze in that 2 pi system between the ends there to do it enterofacially. All right, let's look at this in physical model form, and just bear with me and pretend that we have enough atoms here to represent the entire pi system. This is okay since we only care about the ends of the pi system. And here will be the other reacting component, so the I guess tetracyanoethylene. So I'm going to need to react anterofacial with one piece, suprafacial with the other. And so what I did in my drawing in the notes here is that I took these two ends and I was going to say that I reacted like so, such that I could get in suprafacial with this piece. And so I really had to deflect my ends of the longer pi system to be able to do this reaction. So again, kind of it should look like this, but I'm expecting or requiring that the system deflect a lot in order to geometrically make it possible for my overlap to happen. So of course, anterofacial processes are not very common in cycloadditions, but they again are possible. The reason that we care about this is that the stereochemistry of the carbons around the new bonds formed during cycloaddition will depend on whether the reaction is proceeding suprafacial to suprafacial or suprafacial anterofacial. You can see the impact of that in this example because the anterofacial pushes one of these bonds to be above this ring and the other bond that's formed to be below the second ring here. I want to go over just two more very common types of cycloaddition reactions. The first of these is the thermal 1,3 dipolar cycloaddition, where this 1,3 dipolar term refers to this reacting piece here. This is a 3+2 cycloaddition, and in this cycloaddition what we're getting is that we have a reactant that has a strong dipole to it. In this case, azide has negative charge on one end in the Lewis structure, and it's going to be electrophilic on the other end. So the reaction here I think is very logical to draw out like so. So I'm treating that nitrogen almost like it's a nucleophile, and I'm going to cyclase around, and you'll notice that this last arrow doesn't go all the way through, but it just ends on the central atom to essentially neutralize that positive formal charge. That leads me to having these two new bonds here and here in my product. Again, my 1 and my 3 are referring to the relative positions of the nitrogens here, 1 and 3. This type of reaction turns out to be very, very common and useful for stitching together molecules with different functions. So a very common use is to take a drug molecule with an alkyne on it and do a 1,3 dipolar cycloaddition to attach it to a targeting molecule that has an azide on it. The last type of reaction I wanted to go over is a subclass of cycloadditions. These are called chelotropic reactions, and they refer to the case where a single atom is gaining both of the new sigma bonds that are made during cycloaddition or losing both of the sigma bonds that are lost during cycloreversion. So my example here is a cycloreversion, where if I go through this mechanism, what I'm going to get is that we can essentially think of this coming down to make my triple bond, and then my cycloreversion process to go like so. And so overall what I'm doing is I'm creating my pi system here and then extruding or ejecting a molecule of gas. And so chelotropic reactions tend to be observed often when we are involving the formation, or I guess the consuming of a gas molecule. So that was a look at cycloadditions. We talked about the terminology of going for P plus Q type of a cycloaddition. We also looked at the selection rules, and our main takeaway was that for a 4n plus 2 pi electron system, we would do the thermal suprafacial plus suprafacial reaction, preferably. And for a 4n pi electron system, we would want to do the photochemical suprafacial plus suprafacial reaction. We looked at a few different examples of cycloadditions, and again, we will spend more time looking at the Diels-Alder reaction in depth.